All righty. And so let me do just a couple of quick little things, and so we can see how this works. Let me do my example here. So what I'm gonna have is I'm gonna have my person, me or whatever it is. We're gonna stand on a scale. Okay. So I'm standing on a scale, and we're going to talk about how the scale works. And so I'm not jumping around. And so there is no acceleration as I stand on the scale. We're going to analyze the forces acting on me. And so then we'll have our gravitational force goes, vertically down towards the center of the earth. And this is my weight, which is my mass times the acceleration due to gravity. And then due to contact between my feet and the scale, there will be an upward normal force on me. Okay. Okay, like so. And so then this normal force is essentially on me by the scale. And so then there's a third law paired to that, and that would be the normal force on the scale by me. Okay. And when we talk about a scale like a bathroom scale, then the thing is the way the scale works is the harder you push on it, the more it reads. So this is the normal force on the scale by me. So these are, third law pairs. Look, we actually found some. So yeah. Okay. And the idea here is the harder we push down on the scale, the more the scale reads. I don't happen to have a scale handy, so I can't show that. But I think you know that, as you step on the bathroom scale, the scale reads more. So this gives us the reading on the scale. So the reading on the scale tells you the amount of downward normal force on the scale. And then by Newton's third law, that tells you the amount of upward normal force on you. Okay. And so this essentially is related to the scale reading through Newton's third law. And so this is our more or less our apparent weight. They don't usually talk anything about directions on apparent weights, so that's good. Okay. But yeah, so this upward normal force on me by the scale, which is related to the scale reading, is my apparent weight. Okay. And so then if we were to go in, since there is no acceleration, then I could go in and pick, up to be the positive y direction, and we could run our Newton's second law. So then the net force in the y is 0, plus that normal force on me minus the gravitational force is 0. So then the normal force equals the gravitational force equals m times g. Okay, so this is your scale reading. This is my weight. That's the mass. So they're all kind of hanging out in the same expression. Now what we're going to do is we're going to take the scale and me standing on it. We're going to put it into an elevator. You're like, say what? Well, the thing is that, Einstein talked about it being in an elevator. So amazingly, everybody puts them in an elevator. So there's my little scale. There's me standing on the scale. I'm going to be the object of interest. And then what I'm going to have happen is I'm going to have the elevator is going to be accelerating up. Okay. So we're going to be undergoing an upward acceleration in the elevator. And then when I analyze the forces acting on me, then we get there's gravity, right? Goes, towards the center of the Earth. My mass times G. And then due to the contact between my feet and the scale, there will be this normal force up on me by the scale, which is my apparent weight. And now when we go in and I pick out my coordinate system, let me say that up is going to be the positive y direction. And we write down our Newton's second law. Again, I like to pick my coordinate system to align with the acceleration. Since A was up, then I'll pick up to be positive. And so we would lead off with plus the magnitude of the normal minus the magnitude of the gravity equals m times plus A. So up, up, down, well, same, opposite. That's how it really knows. And then if we put in our things that we know, then I get this is the magnitude of the normal minus mg equals m times a. And then if I move this term to the other side, we can solve for the magnitude of the normal force is equal to mg plus ma. And so again, this is my apparent weight. Is that magnitude of the normal force. And then we get that my weight is this gravitational force, or mg here. And of course, the m is the mass. So you can just see that. So what you're seeing is it's my weight plus this m times a term. Okay. So what you're going to talk about is the fact that if you are standing on an elevator and it accelerates up, the scale reads more. To have a greater apparent weight. So if you get in on the ground floor of an elevator and then hit the up button, what do you experience? What's it feel like? And on the ground floor, hit floor 5 or something like that, and it takes off. What do you feel? Yeah, you feel like you get kind of pulled down into your shoes, right? Like you're getting, somebody's pushing down on your shoulders or you're pulled into your shoes. And in fact, if you stand on a scale, it reads more because that upward force has to be greater than the downward force to create a net upward force to make you accelerate up. So the scale reads more right when you take off. And so really what you experience in the elevator is your apparent weight, that sensation of being heavy or pulled down into your shoes or being pushed down on your shoulders. That is essentially your apparent weight. Okay, that's what you sense. Well, then there's one more case, which is what happens if we're in the elevator, standing on our scale like everybody does, and we accelerate down. Once again, my object of interest is going to be me. Okay. I'm going to indicate the forces acting on me. And so we're going to have our gravitational force, which is my mass times g, and of course is my weight. And then due to the contact between my feet And the scale, we will have our upward normal force, which is going to be my apparent weight. This. And then that should be it because nothing else is in contact with me. So then I'll go in and pick out my coordinate system. I'm going to pick my coordinate system to align with the accelerations like we talked about last time. And since the acceleration is down, I'm going to make down positive. And then we'll write down our Newton's second law in this y direction. I would lead with gravity because it's down and down is positive. So plus the magnitude of gravity minus the magnitude of the normal force is equal to m times plus a. It's this sign on the a that you need to make sure we don't miss. Okay. So it's all good if you want up to still be positive, but you better have the minus sign on that a because the a and the gravity go in the same direction and the normal force goes opposite. So down, down, up. Okay. We put in our values, then this is mg minus the normal equals ma. Move this to that side, move this to that side. Flip the whole equation because, you know, I'm annoying like that. That the magnitude of the normal is mg minus ma. And so then what we see is that with this minus sign is that the scale that we're standing on in the elevator, as we accelerate down, scale reads less. Okay. Now, I have a question. We know that the acceleration is down. Do you know which way you're moving? Or if we know the acceleration's up, do you know which way you're moving? Manuel says no. Yes. Olivia says no. They are both correct. Angelica says no. Knowing the direction of A does not tell you which way you are moving. I mean, just look at the ball, right? I throw it up and I catch it. The acceleration was always down. As the ball went up, it slowed down. As the ball came back down, it sped up. So knowing that A is down doesn't tell me which way the ball went. Now, if you tell me that A is down and the ball sped up, I know exactly which way we're moving, same way as the A. And if you know that the A is down and the ball slowed down, I know the ball went up. Okay. So if we know if we're speeding up or slowing down, then we can determine which way we're moving. Because when we look at the elevator ride, right, you get in on the ground floor and you're going to start off in equilibrium. The scale reading will read your true weight. But then as you head up, then you're going to accelerate up, which means this upward force has to be greater than gravity to create a net upward force to make the acceleration, and the scale reads more. Once you reach cruising speed, then there is no A, even though you're still moving up. And so now the scale reads your correct weight. But now you're moving up and you need to slow down to come to a stop. So then the A has to go in the opposite direction as the upward motion. And so as you come to a stop, then the acceleration's down, net force is down. So therefore your upward force has to be less than gravity because gravity doesn't change. Not over the ride of an elevator, it doesn't. And so all of those things happen. And then when you are at a full stop, it reads true again. So on the slowing down part, what do you experience? So that's either as you're heading up and coming to a stop, or as you get in at the top of the elevator and head down. What does it feel like when you have a downward acceleration as you are in the elevator? I assume we've all ridden an elevator. I guess that might not be true, but I would assume so. What's the experience when we have this downward acceleration? So I think it's easier if you start at the top floor, hit the lobby, and then head down. What do you feel on that initial beginning of the motion when the A is down? Yeah. Yeah, you feel lighter. You feel like the floor dropped out from underneath you. And if you are standing on a scale, it reads less. Now, there is technically an extreme case. That lots of people pay good money for, really. Because if you start off with the fact that your normal force is equal to this mg minus ma, because we're going to do this downward acceleration, then what you'll find is that when a is equal to g, so if a is g, then what you get is that your normal force is 0. And so when a is g, this is when you're in free fall. And when the normal force is 0, then this is my apparent weight. Then I guess you would say that you're apparently weightless at that stage. I mean, this is really what you get for the astronauts in the space station, is they say they're weightless and you see them floating around through the space station, right? There is still a gravitational force acting on the astronauts. That is what holds them in orbit about the Earth. And it's not like gravity from the Earth shuts off at the space station and kicks back on to have the moon orbit the Earth. Because the space station's only like, 400 kilometers up. I mean, if you know where and when to look, you can see it with your eyes. Okay. And so, yeah, if we are in free fall, this was what I had described back in chapter 2, is that if the only force acting on you is gravity, mg, and it's going to cause you to have a downward acceleration, because if there's only gravity, then it's the net force, and net forces cause accelerations due to Newton's second law, right? And then if I go in and I pick that, I'll go, oh, let's pick that down is the positive y direction. And so this is, like I said, this is the, only gravity concept. Then we write down our Newton's second law, then the net force in the y direction is equal to m times ay. You get plus this magnitude of the gravitational force is m times plus a. We put in that this is mg equals ma. And no matter what the mass is, a is g. So all objects accelerate at the same rate in the absence of air resistance if they're in free fall motion. So, questions? So yeah, so the people that go on the, there's the NASA plane where they take up and do microgravity experiments, right? So they take it up and then they drop it, and then they take it up and then they drop it. It's called the Vomit Comet. That would get this idea. If you were on the space station, you would have this experience as well. And in fact, if you go to many amusement parks, then and you do one of the like tower drop rides, right? I don't know what they call them, demon drop, tower terror, something like that. You get into the little box, they take you to the top of the tower, and then they drop you, right? And so you get to experience, free fall for a very short little bit of time. Very often what they will tell you that you want to do is you want to take a coin and put it on your hand or put it on your, your lap. because when you're in the state of free fall, then there is no normal force, which means that there's no contact, and essentially the coin will float right above your hand because you are both accelerating at the same rate together. So then you no longer need contact. So if I'm in the elevator and we're going down at G, then I don't need to actually push down on the scale because we're both accelerating down together. And there is no normal force. Okay. So we would float just like you see the astronauts in the space station because that's what they're doing. They're in a state of free fall.